Let us look at another beautiful question in the same topic from the book Pathfinder. Let's move forward. So, a cylindrical vessel of radius r and height h is fixed at one end of the rod of length L. So, basically, I'll just explain the question here. There is a cylindrical vessel of height h and radius r. It is half filled with a liquid. You are using another rod of length L to rotate this. Okay. What must be the minimum angular speed that you should rotate this so that the water in this does not fall down? Okay. Another thing he's saying is assume that this length is very long compared to the height of the cylinder. Okay. What he means by that is you can take the acceleration of everything in this as L omega square. Centrifugal acceleration, you can take it like that. Okay. Before moving to solving the question, let me just show you something. So this is a bottle of water. Okay. And you observe the surface of water, how it is. Okay. This surface is always parallel with the ground. Okay. That means this surface is always perpendicular to the gravitational force mg. So mg will be downwards. Okay. And the surface is exactly perpendicular to it. Now suppose I tilt the bottle like this. Okay. Even if I tilt the bottle, you see the surface again becomes parallel to the ground or exactly perpendicular to the gravitational force mg. Why does this happen? See, suppose this liquid is like this, it doesn't want to be like this. I take some part of this liquid and put it here. Okay. So how is a liquid now? Something like this, surface is something like this and like this, right? Any system in the world wants to go to its most stable state, wants to go to its lowest energy. Okay. You want to sit in the class or you want to sleep, you would say I want to sleep because it is a more stable state. So even the water here wants to go to more stable state, and that is why if it was here the energy will be more than when it is here, and that is why for the least energy the shape of the water has to be like this, and that is why it is always flat. Okay. Now suppose the water is like this and the earth has moved something like this. So what will happen to the surface? The bottle will be like this, but the water surface will always become perpendicular to the gravitational force. Okay. So this concept we'll be using to solve this question. It's a simple concept. But you see how easy the simple thing becomes while solving this question. Okay. So this is the cylindrical tank in which we have, which is half filled with water. Now let me tell you all the forces here on the water. In this water there was only one force, that was gravitational force. If I start rotating it, if I start rotating this water with respect to this water bottle, there is a centrifugal force. There is also Coriolis force, we won't see that, but there is a centrifugal force which is outside. Okay. So there are two forces in this. One is gravitational force, the second is centrifugal force. Now as this bottle is rotating like this, what happens, tell me, if you are with the bottle, see, the bottle is like this, I'm rotating, I'm going with the bottle, the gravity is downwards, the centrifugal is outwards. That means the centrifugal vector is always going along with the bottle. The gravity is going like this. Okay, the bottle is like this, the gravity is rotating like this. The centrifugal is always outside of the bottle. So what I'm going to show you here is that I'm going to show you all the forces. See, what is our problem statement? No water should come out of the beaker. If this is a bottle and I don't want any water to come out of this bottle, suppose I keep bending it. This is a maximum angle I can bend so that water does not fall. If my angle becomes more than this, then the water will fall out, right? That means I'm saying the angle between bottle and the gravity I'm calculating, gravitational force. Here what we'll do is, we'll calculate the angle between this bottle and the net gravitational force. Net gravitational force consists of two things. One is gravitation and centrifugal force. So let us see how the forces change. If the bottle was like this, the gravity vector is rotating, okay, and the centrifugal force is always outward. The vector sum of gravity and centrifugal force is the net force. So the blue color is the gravitational force, yellow color is the centrifugal force, the red color is the net force. Okay. Now the surface of this water will be perpendicular to which force always? The net force. Okay. It will always be perpendicular to this red vector always. So let us see with respect to the bottle how these forces keep changing. Okay. So you see gravitation is going like this. First we'll see this arrow. Okay. Gravitation force is going like this. Okay. Next, the centrifugal force is always L omega square, because for a given omega, the centrifugal force is L omega square. So this is a constant and it is staying like that. The vector sum of this and this is the red vector, which is the net force. And the water surface will always be perpendicular to the net vector, the net force. Okay. So you see, as this gravitation is going, how is this changing? And we have kept a condition that, see, as it is bending now, the water can come till here, and this vector should come till here and again go back. If this vector goes that side, this water will go this side and the whole water will fall out. And that is what we are going to do. What we are going to do is, what is this extreme case we are going to calculate? And for that we will calculate the angular velocity. So now let us see what is the condition so that water does not fall out. See, this is half filled. So when it is just like this, in the limiting case, this is angle theta, let us say. See, this water surface should be like this, okay, exactly here. Not here, but here. Suppose this is theta. What is this tan theta? If this whole thing is h, and this is 2r, this tan theta, if it becomes greater than h by 2r, what will happen? Tell me. This surface will go like this and liquid will start going out. So in our case, the tan theta, that is very important, the condition tan theta must be less than h by 2r. This is our condition. Okay. So if this is theta, this will be 90 minus theta because it's vertical, and this will be theta. Why? Because our water surface is always perpendicular to the net acceleration. Okay. Now this vector is our L omega square. This vector is G. Okay. Suppose the angle between these two is alpha. Okay. So what is tan theta? Tell me. From this, tan theta will be G sin alpha divided by, just from vectors, okay, G cos alpha plus L omega square. Okay. Tan theta will be G sin alpha by G cos alpha plus L omega square. Now this must be less than h by 2, so that the water does not come out. Now we'll just rearrange the terms. What will we get? So 2rg sin, just a minute. So here what will we get is, I'll take this aside, 2rg sin alpha greater than h into g cos alpha plus L omega square into h. Okay. I can take this aside, and what will I get? 2Rg sine alpha minus Hg cos alpha by, I'm taking this to here, HL. So what we are getting here is omega must be greater than root of this. That means for every angle alpha between the G and this thing, we are getting an expression. Okay. So this omega must be greater than the maximum value of this. Whatever the maximum value, whatever it takes. Okay. So what can be the maximum value of this, tell me? We know from math that the maximum value of a sin theta plus b cos theta is root over a square plus b square. So from this, what we can say the maximum value of this will be, you can just, so 2, I can take g common, g by hl into, so it will be 2r sin alpha minus h cos alpha. The maximum of this will be root over a square plus b square. And this will be the maximum value of omega, so that the water does not fall out from this. Okay.